I'm going to be utilizing this particular reaction to distinguish the difference between a reaction quotient and equilibrium constant, QC and KC. So we have 2 sulfur dioxide and 1 oxygen forming into 2 sulfur trioxide. In the very beginning of the cycle, none of these are made. None of the product is made. You only have sulfur dioxide and you only have oxygen. So you can see that in the corresponding graph that you have some concentration of the 2 reactants. Now, as time passes, you can see the diminishing of the reactant, and that's because those are being utilized. It's being used to make SO3 or sulfur trioxide, and that one is increasing. So in the next beaker, you can see the formation of the sulfur trioxide and diminishing of the sulfur dioxide and oxygen. Now, there is a point in time wherein which the sulfur trioxide or the product and the reactant do not change in terms of concentration. It's as if like the reaction has completely stopped. It didn't stop. In fact, the reactant is being made into a product. At the same time, the product is going back into the reactant. It's going in opposite direction. There's this dynamic equilibrium going on. So it has reached a point called equilibrium. Before or prior to the equilibrium, all of this point in here, we can utilize what is called the QC or the reaction quotient in order to solve the ratio between the product over reactant. At this point, at equilibrium and nothing has changed and at equilibrium and beyond, and there's no particular changing occurring, like say there is a temperature change or more of the reactant is being added, as long as there's no real stress on the reaction in itself, we can utilize what is called the equilibrium constant or the Kc in order to solve for the value of Kc. And that's also product over reactant as well. Let's look at another scenario where in which we have just sulfur trioxide. And then what it's going to do is it's going to be utilized in order to make the sulfur dioxide and the oxygen over time. So that's what's going on here. You have sulfur trioxide being made into oxygen and sulfur dioxide. This also reaches a point in the equilibrium where in which the concentration of the reactant and product no longer changes. So anything before the equilibrium has reached, all of these point in time, we can utilize the QC equation in order to find out the ratio between the product and the reactant. Whereas the Kc, this is when equilibrium has happened. Whether we started from the reactant or whether we started from as a product, as the initial point, it really doesn't matter what the initial point was. In the end, you're going to reach the equilibrium constant, and the value of this one and the value of this one will be the same. So let's go ahead. What is this equation for the reaction quotient, QC, before equilibrium has occurred? The equilibrium constant for this is, or the reaction quotient is, QC is equal to, so I'm at QC is equal to the product, which is the concentration of the product, I should say, to the second power. That second power is coming from the coefficient of the balance equation all over. We have the SO2 to the second power and then O2. Now, I can't put a 1 there. It's to the 1 power since the balance equation there is a 1, but I'm not going to put it. What about the equilibrium constant? This Kc. This looks actually exactly the same as QC. Now, does that mean the value of the QC and the KC will be the same because the equation is the same? No, that's because QC is drawing from the concentration of the points in here, whereas for the equilibrium constant, it's drawing the concentration at equilibrium. So the values of these SO3s will differ, SO2s differ, oxygen will differ, and hence why the value of the QC and the KC will be different. So for the QC, the concentration can be those from or those at any point of the reaction, except at equilibrium. And for Kc, or the equilibrium constant, the concentration must be those at equilibrium. So this is a good point to do a learning check. A gaseous nitrogen dioxide forms into dinitrogen tetroxide according to this equation. So we have that equation here. When 0.10 moles of NO2 is added to a 1 liter flask at 25 degrees Celsius, I should put degrees Celsius here, what is the value of the reaction quotient before any reaction occurs? So it's asking for the value of the reaction quotient, meaning QC, not KC, that would be the equilibrium constant. So that is equal to, if I were to draw or write out the formula, it's the product N2O4 to the first power all over NO2 concentration to the second power. Okay, now and you need to know the concentration of this and the concentration of this. And actually, we do know right away which one it is, but just for the sake of it, let's go ahead and calculate the concentration. So let's calculate the concentration of NO2. So it's 0.10 moles of NO2 and a liter, in a 1 liter. So for molarity for NO2, we need to calculate moles over liter. And so therefore you have 0.10 moles over 1.0. And this is particularly for NO2. And this one's going to be, if you calculate this out, it's 0.10 moles over liter or molarity. Okay, so that value will go under here. 0.10 to the second power, and now we need to find out the concentration of N2O4. But you see over here, it's like, okay, I don't see any information about that. Well, what is the value of the reaction quotient before any reaction occurs? Meaning that you only have the concentration of the NO2. So if I were to go back into this graph here, it's at this point right here where in which you only have the reactant and none of the product. So if you have 0 product, that means there's 0 concentration. If you have a 0 numerator, then automatically the QC becomes 0. So the value of the reaction quotient before any reaction occurs, that would be a 0 because there is no product. Now it's asking for what is the value of the reaction quotient when there are 0.063 molarity of NO2 and then 0.02 molarity of N2O4. Try to set this up and even calculate and come back and check this video. So here is the setup and let's do the calculation. We have 0.012 as a numerator and divide that by, I'm going to give a parentheses, 0.063, and that's to the second power. I'm going to close that parentheses to let the computer or the calculator know that the second power is for the 0.063. Hit enter. and I get 3.02 or 3.0. And that's the reaction quotient for this particular concentration of the reactant versus product. Now it says at equilibrium, the concentration changes. And so that you get NO2 is 0.016 and N2O4 is 0.042. What is the value of the equilibrium constant? So that's Kc for the reaction. Kc here is the same equation as Qc. This is O4, and then all over NO2 to the second power. Press in the corresponding values that is associated with it, calculate, and come back and check the video. Okay, so you can see on this calculator, it's about 164. Since I want to keep it at correct sig figs, I'm going to put it as 160. 160. Note that the value of the Kc is significantly higher than the Qc. In a case like this where the Kc or the equilibrium constant is higher than Qc, that means this particular point in which we calculate the reaction quotient, it has far ways to go to form a product. It's on its way to form a product. So something to look forward to in the future videos about the interpretation of between the Kc and the Qc when it comes to value. I'd like to compare reaction quotient Qc and equilibrium constant Kc in this video.